you will increase the TIT, also increase the pressure ratio, but much less, because it's remaining at a low pressure ratio. So if you want, when you need to have a lightweight engine, you will have, let's say, a small compressor. What seems to be rather logic, but it's obvious when you look at the thermodynamics. And like this, you can define your design point. You define your design point. Okay? So you say, okay, I will choose this TIT, I don't know, 1050 Celsius, I don't know. And I will choose my pressure ratio, I don't know, 15, for example. Of course, for some design conditions, here in this case, this is 0 the speed, but for some atmospheric design conditions, where this is valid, where everything that you have explained is valid. And for that, you will find a P over m dot that will be equal to a certain value, and you will have eta E that is, for example, equal, I don't know, to 39%. I don't know. What is the type of eta E that you can reach with this basic gas turbine engine? Let's say around 40%. Depending on the size of the engine, the age of the engine, etc., you can be at 38, 39, 40, 40.1 or something percent. If you are at 40%, it's already a quite advanced engine with a basic gas turbine cycle. You will be most probably a bit lower than 40, or much lower than 40 if it's an old engine. Okay? But like this, you can design, you can choose your design point. Again, you will be mainly, very often, outside of the design point, so the selection of this point is not so important. But you have to choose one, and after that, look at how this point will influence the performance outside of the design point. And so you see that for discussion, working in compressor temperature ratio, theta is a bit useful, even if this parameter will not be so often used in this course. Okay? And eta E, let's say, just lower than 40% is already a quite good one. Of course, we see that we cannot optimize both performance at the same time. So you see, if I represent it here downstairs, so you will have for eta E a curve like this one, and you will have for P over m dot a curve like this one. And you see, if you select this pressure ratio, you will have this that is maximum, but this one is much lower than the maximum. And if you select this point, so this pressure ratio PC2, you see that eta E will be maximum, but this point is much lower than the maximum here. So we need to choose, if we want a lightweight engine, it will burn not so low amount of fuel, and if you choose an engine that is burning a low amount of fuel, it will be rather heavy. And that's why very often you will go more in this zone for the selection of the design parameters. Because if you choose a point that is there, a PC3, you see that you are, for example, in this point. And in this point, of course, you are burning more fuel than there, but not so much more. And of course, you are heavier than here, but not so much more. And so maybe that the trade-off should be there in between. That will not give you the lightest engine, not the lowest amount of fuel burn, but the best trade-off, the best compromise in the choice. Okay? Globally speaking, very generally speaking, we will go for transport aircraft more in this zone. So a trade-off between fuel and weight. If you have long-range aircraft a bit more to the right, because you are burning fuel during a much longer time, and if you have a medium range or a short range a bit more to the left, because you are burning less fuel, and so the fuel is becoming less and less important compared to the weight. And there are some engines that are here. It's existing. Engines that are optimized not for the fuel burn, just for the mass. These are engines that are used during very short time. If you have a flight of 10 hours and that there is something on board that is used during, let's say, 5 minutes, what is the importance of the fuel burn during 5 minutes compared to 10 hours? So, for example, here you will find the APU, the auxiliary power unit, what is used to start the engine or to generate electricity on board when you are not connected with the grid on an airport. I will explain you later on what is an APU. Also, you have the engines of missiles. So there are some missiles, so let's say this is an armament. Okay, I know that we are not military people, but this is existing. So missiles that have a long range, for example, cruise missiles, or for example, anti-ship missiles, they have on board, in order to increase the range, they have on board a small gas turbine engine. This small gas turbine engine will be used during what? 30 minutes? Maybe 10 minutes? A few minutes? I don't know, much less than 1 hour. And the fuel burn is not very important. It must be small, because the missile is not huge. It has a small diameter. And also it must be light. So there are applications where we are aiming at minimum mass. I give here 2 examples with the APU, auxiliary power unit, or the GFS that we will see later on, the jet fuel starter. So the GFS is also an example that we will see later on, and that are engines that are optimized for this point. Whereas most engines are optimized here in between, a bit more like in this direction for long range aircraft and more in this direction for short range aircraft. Okay? Now, we have seen the design computation. We have done the optimization in order to find the design point, the optimization that we have here. And we need to look at the third step, which is the off-design. The third step, which is the off-design computation, off-design computation. Off-design, that means you have selected your design point, and this is what I had explained here. You have selected your design point. What's happening if the pressure that you have considered during your design computation and your optimization is changing? or the altitude, if you want. What's happening if TA is changing? VA is 0. Also, the relative humidity can be a factor that we have very often neglected. And also, if you change this, what will happen in your system? So, and this is very summarized, very well summarized in the position of your gas handle. So TIT and the pressure ratio, these two parameters, when you have selected the compressor, they will be closely linked. We will see that later on. I cannot explain that in the details today, but in fact they are closely linked when you have selected a certain compressor. And they are related to your gas pedal, like in your car. That is, in an aircraft engine, the throttle that you move in front of you in an electricity production unit, or in an aircraft that you push in a civil transport aircraft with your right hand, and that you push in a military aircraft very often on your left hand. So this is a parameter that I will summarize very often like what is called the PLA, the power lever angle. So the position of the gas handle, of the gas pedal, of the throttle. Okay? And PLA is a physical parameter. This is the position, as in your car, of your foot on the gas pedal. In a gas turbine engine, it can be expressed in a lot of different ways. It can be the TIT. It can be also the fuel flow. The fuel flow is a way to express the position of the gas pedal. It can be the pressure ratio when you have selected a certain compressor, and it can be a lot of other things. For example, it can be also related to the mass flow rate entering into the engine. Because when you will change the position of the throttle, you inject more fuel into the system, and everything is changing. And very often, we will characterize the PLA, I write it with an equal, with the rotational speed. Why? Because the rotational speed is a parameter that is very easy to measure. It's very easy to measure the rotational speed of a shaft. Very, very low cost, very easy, and the sensor is reacting very quickly when you change the rotational speed. Whereas when you change the fuel flow, so it's more difficult to measure. It's more difficult to measure a m dot. It's impossible to measure a TIT. It's very difficult to measure pressure ratio. So these parameters are in theory possible, but the only one that is practically possible is the rotational speed. And so what do we mean when we say that we will change the design, that we will change the working conditions, the work